Hi, I'm Ahmed Daud, and in this session we are going to start decision trees. So this session will be type of introductory session, and we will discuss some technical aspect in the coming sessions. Uh, Here you can say a tree, which is I have drawn in opposite direction, because to simulate and to give us some similarity with the decision trees. So this same type of flow decision tree follows the root on the top side, and their branches and their leaves are on the bottom side, and in that way actual decision tree grows. Like if I will show you in this way the decision tree structure usually. Okay, in this way it grows. The root on the top side, and their branches, their leaves are growing towards the downward. Okay, so decision tree is a non-parametric model, and you know about that because I have told you in the previous session. So in these sessions you will learn how actually non-parametric models work without following any assumption, without following any mathematical relation between inputs and output, how it draws some patterns from the data set. Another aspect is there is a one famous algorithm, and it is a quite powerful machine learning algorithm, random forest. So the base of random forest is decision tree. So if you will be have some good understanding of decision tree, you will be able to crack random forest uh, more, you can say, in good manner. So actually decision tree extracts some rules from training data, and this is also the way of a non-parametric model. It directly extracts some patterns from the training data. So I will start from a simple example. Let's say here you have four animals. You have some data set, and you have four animals or four classes in your output variable: bears, hawks, penguins, and dolphins. So you have to build some rules. On the base of that rules you can distinguish between bears, hawks, penguins, and dolphins. Now you have to draw such type of rules that can narrow down uh, uh, your number of classes into some partitions. Let's say first of all you will ask a question like that: uh, what are the animals that has feathers? Let's say if I will say what are the animals that has feathers. Okay, so the animals that have feathers will be on the left side, and the animals those have not feathers will be on right side. So hawks and penguins have feathers, while on the other side bears and dolphins don't have any feathers. Now again we have to ask such type of question, or we have to draw such type of rule that can distinguish between these two groups. Let's say here I can ask a question: what are the animals out of these two that can fly? Okay, so here you will say hawk can fly, but penguin cannot fly. Okay, here again you can ask a question: what are the animals out of these who have fins? Okay, so you can say here dolphins have fins while bears don't have. Okay, so in that way you have asked some questions, or you can say you have some rules on drawn from your training data, and you build a site type of a decision tree. Now whenever a new data point will come, you will ask same question, that particular data point has feathers. If have, then you will go towards this side. If don't, then you will go towards the this side. Okay, again you will ask question, and until you will reach your class. Okay, so if I will show you more, a good image, you can see that way. Okay, so this is the more theoretical explanation of decision tree. We have to set some rules from the training data, and then we have to build a decision tree on the basis of that rules that can narrow down your number of classes, and you can in that way you can whenever you have to do some prediction, you can follow the pathway. You will ask the question, and according to the answers of the question, you can reach to your predicted class. Okay, so now uh, we will go towards the more towards another example in which we will have two independent variables x1 and x2. Both are numerical. Both have numerical values, and we have two type of classes: blue points and red points. And if I will ask you the question, or I will ask you to do that, partition that number of points in that way that each subspace will have similar type of data points. So what you will do, your brain automatically start to think in that way. If I will split from this point, then there will be no such group that can if I will split, let's say I will split from this point, you can say that you are not splitting the data points in that way that on the one side there are blue points and on the other side there are red points. Okay, so you will find such type of partition in which on the one side there will be same type of number of points, and on the other side there will be another type of data points. So the more good partition will be like this, in which there will be more data points, red data points on this side, on the uh, uh, side when there is x2 have values less than 0.4. There will be more data points, red data points on the left side if I will make it true, and if I will make it false. So there will be more data points, red data points on this side, and more blue points will be on that side. So these are again not pure. Again, we have to split these two spaces. Now we have these two partitions. Let's say this is partition 1 and this is partition 2. Now each partition I have, again there are some blue points and some on the partition 1 there are some red points. Now again, if I will ask you that split your partition 2 so that you will have on in one partition just same type of number of points, so you will partition in that way. Okay, so there is more data points, red data points are here, and here are blue data points. Okay, in the same way, if I will ask you to partition or to draw a boundary between in the partition 1 so that one subspace will hold same type of data points, you will probably draw a line from here, and this you can call it as a red points, and this you can call as a blue points. Okay, so here you can see, if I will remove this one, okay, you have here decision boundaries, and you can get an idea that these are not all the pure points like in this decision bound, this subspace. Let's say this is a if I will give the name, this can be a partition 1, this can be partition 2, partition 3, and partition 4. So again, all the partitions are not fully pure. There are like in the partition 3 as it belong to red points, but there are some blue points also here. But we have to draw such type of boundaries which should be generalized boundaries. Okay, we don't have to draw boundaries like these that can be type of very tight boundaries. Okay, so we don't have to do that. Okay, if I will draw a decision tree, x2, the points that have x2 values less than 0.4 are this and this, and again I will can say the points that have x1 value or less than, let's say, 0.7, or the if this is true and this is false, so this can be called as a red, and this can be called as a blue. Okay, again you will ask a question on the base of x1 to again split your partition that is only having data points greater than 0.4 for the x2 feature. So x1 greater than 0. Sorry if I will follow the same way. X1 less than 0.5. If true, then on this side, and if false, then on this side. Okay, so here you will say that these x1 having values less than 0.5, these are the blue points, and these are the red points. Okay, now here you can get an idea. I have drawn a decision tree from these data points directly. Okay, so here you can say you can see these partitions, these decision boundaries, because you have just two independent variables. When you have multiple independent variables, let's say more than three, or independent variables, four, five, six number of independent variables, then you are not able to visualize these data points in that way and can draw decision boundaries in this way. But on the other side, if you follow the decision tree, then you will be able to draw a decision tree for the multiple independent variables. Okay, and also for the classes when you have more than two classes also. Now, here, this you can say this is restricted towards the very low dimensional data set, and but this is the you can draw multiple dimensional decision tree. Now, how actually you will draw, or you can build a decision tree by using the training data points. You will follow the same way like you did uh, in the case of these two independent variables. You have started from like your brain works in that way. You have started from thinking from all the data points at which all the values of x1 and x2, that at which point we should split the data points so that we can get more uh, pure decision boundaries. We can get the decision boundaries that can have uh, uh, that can split the data points in that way, that one on the one side there will be similar type of points, and on the other side there will be some similar type of data points but belonging to other class. So we actually, in technical aspect, we actually calculate the homogeneity, or you can say heterogeneity. At each point we calculate homogeneity, that if I will separate from this point, what will be the homogeneity of upper partition and bottom partition. If I will separate from this point, what will be the homogeneity of the upper part and the lower part. What will be the homogeneity if I will separate from this point where the value is 0.7 of x2. What will be the homogeneity of the upper partition, and what will be the homogeneity of the lower partition. Okay, we calculate the homogeneity, or you can say heterogeneity, at each point, and which will give us more pure partitions. We will follow that partition. Okay, so uh, what I mean by homogeneity and heterogeneity, let's say you have this box in which you have, let's say, 5 points, 1 2 3 4 5, five blue points. Now I can say that this set of points is purely homogeneous. Okay, you can say homogeneous and also you can use the word pure. So this set has pure points belonging to blue class. Let's say there is one another point which is belonging to that yellow color. We can say now it is not fully pure. There is added some impurity to that set of points. So there is a little bit, or you can say there is a little bit impurity in that. Little bit impurity this box have. Okay, so if there will be instead of 1 point there will be again 5 points belonging to that uh, yellow class, you can say this is a very impure, which this set is very impure, that have 5 points belonging to the yellow class and 5 points belonging to the blue class. So in that way you can say that homogeneity or homogeneity or pure set of points can be belong when we have similar type of points. When we have some other points or belonging to some other color or some other class, then we can say our set is not fully pure. Now our set is impure. Okay, now this strength of impurity, how we can calculate this strength of impurity? There are some impurity measures that can be able to give some numerical value, that like previously, if the set have all points belonging to the yellow class, or the some impurity measure can say that this set have zero impurity. When we have a set which have uh, a little bit impurity, then it can say that this has zero point 0.1 impurity. And when we have a set when we have, let's say, equal number of impurity, then it can give us the value that like 0 0.9, which shows that this set is very impure. Okay, so there are some impurity measures that we can use, that can tell us some numerical value that can explain the impurity in the set. Okay, and that impurity measures we will learn in the next session, but for now you can get an idea that you can get an idea that from each point we will see that if I will subtract from this point, what will be the impurity on the upper portion and what will be the impurity of the lower portion. If I will subtract from this point, what will be the impurity of the upper portion, what will be the impurity of the lower portion. In that way, we will check against all values of x2 and against all values of x1, and which value will give us the lower impurity, which will give us the lower impurity value against some impurity measure. We will select that value as our first partition. Okay, in the same way again we follow the same rule or same technique for the further subpartitions. Okay, so that more practical example we will see in coming session after discussing the impurity measures. In coming session, we will discuss some example. If you are not getting clear and understanding till now, it is pretty much you can say there is no much problem. You will get you will see an example, and you will get more clear idea about the decision tree, how it follows, how the algorithm of decision tree actually works. Okay, but this session is type of introductory session in which we are just discussing what is the decision tree, what type of structure it actually have, what type of method, what type of algorithm it usually follows, and you get an idea that there should be some impurity measures that can calculate the impurity in a set, so that you got an idea that there should be some impurity measures that we will learn in the coming session. So for now, Decision tree algorithms, there are multiple decision tree algorithms like ID3, C4.5, C5.0, CART algorithm. Like ID3 algorithm, this algorithm can build a multi-way tree, means it can split your actual points into like it can build multiple branches. Okay, but here you can see that the tree that we are till drawing have just two branches at each node. Two branches have each node, like we are splitting in two branches at each node. But ID3 can build a such type of tree which can have multiple branches. But their limitation is that in ID3 that features must be categorical. It means that it cannot be able to work on the numerical independent variables. There is another version of that which is C4.4, 4.5. It is successor of ID3. It removes the restriction of only categorical features. This is able to also cater the numerical independent variables. There is another algorithm which is C5.0, which is more optimal version of C4.5. Like you can say it uses less memory, builds smaller rule sets, and more accurate. And it can also work on the categorical or numerical independent variables. But these three algorithms that we have discussed till now, ID3, C4.5, C5.0, all can work for the classification problems only. Okay, so there is another algorithm called algorithm that can work both for the classification and regression problems, and it can also cater both categorical and numerical, or you can say continuous independent features. Okay, but it is restricted to the binary tree. It can only grow binary tree which will have two branches at each node. Okay, it cannot have a multi-way tree. Okay, so this is one of the, you can say, property or whatever you can say, but it can generate only binary tree. It can work for both classification regression problems. That's why their name card is also for the same case, classification and regression tree, CART, card algorithm. Okay, and sklearn, scikit-learn library that we are using till now, and we have imported almost all the models and all machine learning part from the scikit-learn, and we are using that library particularly in that course. So it sklearn also use the cart algorithm. Okay, uh, uh, it actually used the card algorithm with having some changes in actual concept of card, but follows the same type of flow of card algorithm. If I will show you the documentation of sklearn, you will get more good idea. Here you can see this is if I will show you from here. This is the documentation provided by the scikit-learn, in which it tells you all the about the decision tree, classified decision tree, regressor, their advantages, disadvantages, how they have the scikit-learn has implemented the decision tree in their class sklearn.tree.decision tree classifier. So if I will go towards this, I have gotten the information that I am sharing with you, ID3, C4.5, 5.0 card from this documentation, and you can read that documentation along these lectures. You will get more good idea how scikit-learn following the way. Okay, and if I will show you from here advantages and disadvantages, let's say from the start, in the advantages and disadvantages and in the whole documentation, it also tells you that what are the features or what are the aspects that scikit-learn has not till you can say implemented. Like for example, here you can see this second point, which is showing that actual card algorithm or actual decision trees uh, does not affect decision tree does not affect by the missing values. But till now, scikit-learn module cannot do that, cannot support missing values. We have to treat missing values before to feed the decision tree that is implemented in scikit-learn. Okay, so always there is some in the theoretical concept and in some practical implementation there is some difference, because in practical implementation you have to see some other aspects like a computation power, your resources, your you can say complexity, time complexity, uh, or some other aspects. So always there is usually a gap in between theoretical concepts and practical implementations. Okay, so we will along the this module we will see all of that, how scikit-learn has implemented, how scikit-learn implement, or you can say build decision tree by using card algorithm. So in the coming module, we will have a look on the impurity measures, how we can calculate the impurity for a given set. For now,